Hello students, let's continue with ionic equilibria. We have seen what we mean by weak acid and weak base. Now we will study today Ostwald's dilution law for the same, dissociation constant for weak acid and weak base. Let us see what it is. Weak acid we know is represented by Ha. H because it is an acid, and this will dissociate to very less extent to give you H plus and A minus. And according to the law of mass action, the dissociation constant for acid Ka is given like this. You will first write products and this will be divided by Ha, that is reactant. This Ka is called equilibrium constant or acid dissociation constant. So you are supposed to remember acid dissociation constant Ka for weak acid is given by this equation. Similarly, weak base was represented by BOH. You must have OH in the formula, and because it is base, we are having this prefix B. So BOH dissociates to very less extents to give you ions like B plus and O minus, OH minus, and the base dissociation constant, that is Kb, is given by this particular reaction where we have the ratio of products to reactants. So you must remember the dissociation constant Ka, and for the dissociation constant for base is given by these two equations. Now very important law based upon this dissociation constant is called Ostwald's dilution law, and we will be seeing this Ostwald's dilution law for weak acid, and it will be very similar when we come to weak base. Weak acid represented by Ha is giving you H plus and A minus, and Ka, that is acid dissociation constant, is given by this equation. Now we have to consider that in a volume V, in a container which is having volume V liter or V dm cube, we are taking 1 mole of this weak acid, and this will dissociate very slowly. Suppose alpha is the fraction out of the 1 mole which is dissociated. So what remains undissociated is 1 minus alpha. I am repeating, in a container having V dm cube volume, you are taking 1 mole of the weak acid, and from this 1 mole, alpha is the fraction of the acid which dissociates. So the fraction which remains undissociated from 1 mole will be 1 minus alpha. I am writing this equation again. So initially the moles present was 1 mole and the products formed were 0. Now at equilibrium, the moles left from Ha will be 1 minus alpha, because alpha is that fraction which dissociated, and what H plus you will be having alpha, and A minus is also alpha. Equal amount of this will be formed. Now we know moles per dm cube, which is also called concentration, is given by 1 minus alpha dividing by the volume of the container or the total volume of the solution. So all these we divide by V, that is the volume of the container in which we have taken 1 mole of Ha. Now Ka, from this particular equation, H plus value is alpha upon V. So we are substituting. A minus value is also alpha upon V. We substitute. And Ha, as you can see in equation 1, in denominator, Ha we will substitute as 1 minus alpha upon V. So alpha into alpha will be alpha square. One of the V is getting cancelled. So you are left with 1 minus alpha into V. We know that concentration is just the reciprocal of volume, or it is inversely proportional to volume. So this 1 by V can be substituted as C, which represents concentration. Now, as already said, Ha is a weak acid, so very less amount from this will dissociate, which means alpha is very small. So 1 minus alpha is approximately equal to 1. So if I write 1 minus alpha as 1, this factor will be removed and you will be left only with Ka is equal to alpha square upon V, because this is equated to 1, and 1 into V will be V. So what is alpha then? It will be the square root of Ka into V. Ka multiplied by V will be alpha square, and alpha will be equal to square root of Ka into V. We know that V is the reciprocal of C. So instead of V, I can also write 1 by C. So when concentration and acidity constant is given, you can find out alpha. So we learn that the degree of dissociation, that is alpha, is inversely proportional to square root of concentration, and it is directly proportional to square root of the volume. Same, we are having this Ostwald dilution law for a weak base. We know weak base is BOH, which dissociates to give B plus and OH minus, and the base dissociation constant Kb is given by this particular equation. This equation again I am writing, and the way we have done in with weak acid, we are doing with weak base. Initial moles of BOH we are taking 1. So at the start we don't have any product, so this is 0. At equilibrium, what will be left from 1 mole of the weak base is 1 minus alpha, and B plus will be alpha, OH minus will also be alpha. Because I want here concentration to substitute in this particular equation, just divide this moles by volume of the solution. So Kb was given by this particular equation, in which I will substitute B plus value. B plus is alpha upon V, substitute here. OH minus is also alpha upon V, substitute. And BOH, you can see BOH is 1 minus alpha upon V, which we take in the denominator, and alpha into alpha is alpha square. One of the V is getting cancelled. You are left with this, and arguing in the same way that alpha is very, very small for weak base. 1 minus alpha is almost equal to 1. So this factor again disappears, and you are having only alpha square upon V. That means Kb into V will be equal to alpha square. So your alpha will be equal to square root of Kb into V. That means degree of dissociation is directly proportional to square root of volume, and we know volume is inversely proportional to C. That is V is equal to 1 by C. So you can write Kb divided by C. That is degree of dissociation is inversely proportional to square root of concentration. That's all for today. See you in the next class.